This is Rosen, Discrete Mathematics and its Applications, Introduction to Section 2.4 on Sequences and Summations. These are the topics contained in the section. We'll cover sequences in this video. All right, so what is a sequence? How does it differ from other structures we have encountered? Well, basically, it's an ordered list of elements. Recall that sets are a collection of elements that are unordered and in which repetition is irrelevant or immaterial. In sequences, the order is important, and if repetition occurs, that is also important. You'll find that sequences arise in a number of places, especially with functions from the integers. And well, we'll begin. Okay, so a sequence, as I mentioned, is a function from usually a subset of the integers, starting with 0 or 1 and going up, either the non-negative or the positive integers, to another set S. And that the integer that gives rise to the values in the sequence is often denoted as an index to the sequence, but you can also think of it as the argument in a function. And here is the from set in this particular case. And then each term in the each element of the sequence is called a term. Here's an example. My from set in this case is going to be the set of positive integers 1, 2, 3. And then I do have a function that I apply that to. It's going to be 1 over n. And so then I can write down, and the sequence can be represented by just a curly brackets with the a sub n, as long as the n set, the set from which n comes is understood. And here's the beginning of that sequence. 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so forth. We have two different types of progressions that we'll define. One is the geometric progression. And in the geometric progression, the sequence looks like a number a, and then a number a times ar, then a number a times ar squared, such that successive terms of the sequence always have a ratio of r, or 1 over r, depending on how you make the division. So the initial term is called a, and the common ratio is called r, all real numbers. Here's an example. The initial term is 1, and r is -1. And we'll see that that will look like alternating series of 1s and -1s. So 1 times -1, in this case, we're mapping from the non-negative integers. So this is 1 times -1 to the 0 power. This is 1 times -1 to the first power, and so forth. So it's going to alternate 1, -1, 1, -1. If we take a to be 2 and r to be 5, then we will continue to have our domain be the set of non-negative integers, so it includes 0, 1, 2, 3, 4, and so forth. And then 2 times 5 to the 0 is 2, 2 times 5 to the first power is 10, 2 times 5 squared, or 2 times 25 is 50, and so forth. And nothing says these have to be integers. These come from the real number. So here we'll have the common ratio be 1/3, the initial term be 6. So again, our from set will be the non-negative integers. 6 times 1/3 to the 0 is 6. 6 times 1/3 to the 1 is 2. 6 times 1/9 is 2/3, and so forth. And that's geometric progression. The next series is called an arithmetic progression. And in this series, instead of having a common ratio, each term will have a common difference. We do have an initial term a, and the next term will be a plus d, and the next term will be a plus 2d, and so forth. So again, those are called the initial term and the common difference. So if a is -1 and d is 4, then the mapping from the set of non-negative integers will have -1 plus 0 times 4, essentially, and then -1 plus 4 is 3, -1 plus twice 4 is 7, and so forth. And if a is 7 and d is -3, you'll see that this will be a declining sequence. So 7 minus 3 is 4, minus 6 is 1, minus 9 is -2. And here we have a progression of the positive odd integers. A is 1 and d is 2. And those are two different types of sequences, but there can be many other types, but we will encounter geometric and arithmetic progressions regularly.